A very good day to Dr. Ruhaila. We are Group 5 and we will be presenting High Performance Liquid Chromatography HPLC for our video assignment. Our group consists of 5 members, which are Stephanie Valerie, Nur Farahia, Sarah, Norberia Izet, and Norwa Fishukrina. Our roles are stated under our names respectively.
Hi, I'm Stephanie and I will present about the introduction of HPLC. So what is HPLC? HPLC stands for High Performance Liquid Chromatography and it is a powerful analytical technique used to separate, identify and quantify components in a mixture. The principle of HPLC involved the use of liquid mobile phase to carry a sample through a packed column where separation occurs based on the interactions between the sample components and the stationary phase within the column. There are some principles and concepts that we can see here, which is stationary phase, mobile phase, injection, retention time, and column efficiency.
Hello, my name is Noah Fisher-Grina and I'm going to explain about the methodology part in terms of sample preparation. Before that, I'm going to show you the chemicals needed to make these samples. There are two types of samples we'll show later. The first one is stock solution, which is caffeine, and the second one is soft drink sample. But in this video, it shows tea sample. Actually, I changed it to soft drink instead. So these are the chemicals will be used in this experiment. First thing first, we will add the stock solution, which is caffeine, into the volumetric flask and refill it with distilled water until it reaches the mark. Then, seal the volumetric flask and mix the solution well until it's homogeneous. Transfer the solution into the shrink that attached with the filter and the solution was filtered into the gas tube. After that, from the gas tube, the solution was transferred again into the HPLC tube like this. Next is for the soft drink. As I mentioned before, the sample was changed from tea sample into the soft drink sample. So the soft drink sample was filtered into the glass tube using the shrink and the filter, and the sample was transferred into the HPLC tube. The sample with different concentration was obtained and transferred into the HPLC tray like this. Then, put the tray into the HPLC machine for the next method, which is injection.
The sample analyzed, let's move on to data analysis. First, click Result under the Reprocess section. Now, it's time to process the chromatographic data using specialized HPLC software. This step is crucial to ensure accurate and reliable results. The software will analyze the peaks, integrate areas, and provide quantitative data on the caffeine concentration in the samples. Moving on to the next step. Next, click Disable Peak Detection and set marker at the far left. This step is important to improve the accuracy of data analysis. Now, click Enable Peak Detection and set marker just before the peak. This allows the software to mark the peaks in the chromatogram. Next, click Disable Peak Detection again and set marker right after your peak. If you encounter unexpected peaks or interference in the chromatogram, it's crucial to investigate and identify the sources. Click Reprocess to analyze your peak. Once the data processing is complete, the next step is to generate a comprehensive report. Press Return, File, Print Preview Report, respectively. This report will detail the caffeine concentration in the samples based on the calibration curve established earlier.
Hello, my name is Sarah and I will explain the result of the analysis for this experiment. The soft drink sample that we used was Cola Isma. From the chromatogram that we obtained after the samples went to the HPLC, we are able to record the retention time and the peak area for caffeine. The retention time for caffeine standard was 0.849 minutes and the peak area of caffeine was 100%. The retention time of soft drink samples that are run once, twice, and thrice were 0.815, 0.828, and 0.827 minutes respectively. The peak area of caffeine for the samples are 50.8646%, 42.3010%, and 49.6316% respectively. These are the chromatograms that we obtained after the samples went through the HPLC. The peaks are shown in the chromatogram and it is interpreted as the retention time. Next, we'll move on to the calculation topic for our discussion. We will calculate the response factor RF, and then the RF that was calculated will be put into another formula that will be used to calculate the concentration of caffeine in the unknown samples. To calculate the RF, the peak area caffeine standard was divided with the concentration of caffeine standard. The concentration of caffeine standard, which is 0.1 mg per milliliter, will be converted into 100 parts per million. The peak area caffeine standard was 1.13104 times 10 to the power of 4 milliabsorbance unit. It was put into the formula of RF and the value obtained was 113.104 milliabsorbance units parts per million. For the concentration of caffeine in the unknown samples, the peak area caffeine in the sample was divided with RF. The values obtained after dividing the peak area caffeine in the samples with RF are shown in the slide, where the concentration of caffeine of soft drink sample that are run once was 42.03396 parts per million. The concentration of caffeine of the sample that are run twice was 127.72581 parts per million, and the concentration of caffeine in the sample that are run thrice are 141.94458 parts per million. That is all from me, and the discussion will be continued with the topic of advantages and limitation of HPLC.
Hi, my name is Nova Josephi, and I will continue the next part of our discussion on HPLC. As a powerful analytical technique widely used in various scientific disciplines, including chemistry, biochemistry, pharmaceuticals, and environmental science, HPLC has both advantages and limitations. Some of the advantages are, firstly, high sensitivity and precision. HPLC provides high sensitivity, allowing for the detection and the quantification of trace amounts of compounds. It offers excellent precision, making it suitable for accurate measurements. Next is versatility. HPLC can be applied to a wide range of compounds, including polar and nonpolar substances. Thus, it is effective for separating both small and large molecules, making it versatile for different applications. Thirdly, speed and efficiency. Compared to some traditional chromatographic techniques, HPLC is relatively fast, with analysis typically completing within 10 to 30 minutes. The use of a pump for solvent delivery enhances the efficiency of the separation process. Other than that, automation in HPLC systems reduces the likelihood of human error, ensuring reproducible results. The technique is amenable to automation, allowing for high throughput analysis. Next, we have high resolution. HPLC delivers high resolution separation, enabling the distinction of closely related compounds. It is particularly useful for complex mixtures with multiple components. Lastly, HPLC is well suited for quantitative analysis, providing accurate concentration measurements for identified compounds. Moving on to the limitations of HPLC. HPLC can be expensive to set up and maintain, requiring specialized equipment and consumables. The use of organic solvents, which can be costly, adds to the overall expense. Next, sample size. HPLC typically requires small sample volumes, which might be a limitation when dealing with limited sample quantities. Other than that, developing new HPLC methods can be challenging due to the need to optimize various parameters, including columns, mobile phases, and detectors. Troubleshooting issues can also be complex. HPLC may have low sensitivity for certain types of compounds, leading to challenges in their detection. Some compounds may irreversibly adsorb to the stationary phase, resulting in their poor detection. HPLC systems require regular maintenance to ensure proper functioning. Instrument downtime for maintenance or repairs can disrupt workflow in analytical laboratories. And last but not least, HPLC is not ideal for the analysis of volatile compounds, as gas chromatography is often more suitable for this purpose. In conclusion, HPLC is a versatile and powerful analytical technique with numerous advantages, but it also has limitations that should be considered when selecting the most appropriate method for a given analysis. The choice between HPLC and other chromatographic techniques depends on the specific requirements of the analysis and the characteristics of the compounds being studied.
As for the conclusion, HPLC stands as a fundamental and versatile analytical technique with widespread applications across various industries. Its principles and concepts revolve around the efficient separation, identification, and quantification of components in complex mixture. As for the advantages of HPLC are multifaceted and contribute significantly to analytical efficiency and precision. HPLC offers rapid and accurate separation, allowing the identification and quantification of diverse compounds in complex mixture. That is all from our group. Thank you.
These are the references that we used for our video assignment. That is all from Group 5, and thank you so much for watching.